In this session, our focus is going to be chemical reactions and calculations involving chemical reactions. So in this regard, we'll talk about writing chemical reaction equations in the correct format, balancing them, which is a very important part of this whole process, and talk about stoichiometry, that is just a fancy way of saying chemical calculations using reaction equations. We will end this session, set of sessions with limiting reactants and theoretical yields and percent yields. This whole calculations, that when we get there, you will notice they're very similar to the ones we've already done, but in a slightly different context. Okay, so let's get started with a chemical process. What is a chemical process? Does anybody remember that? If you remember from a while ago, a chemical process is a process that changes the chemical identity of a substance when that process takes place to create substances that are new, that did not exist before. Any process that involves consumption of chemical consumption of whatever we started with and creation of new substances is called a chemical process. So chemical reaction equation is basically a representation of a chemical process, when a quick way of writing whatever is happening during a chemical process is a chemical reaction equation. Now this next point is extremely important. Whenever we write chemical equations, we must use the correct chemical symbols of or formulas of the substances. So it is very important for you to know the correct procedures for writing chemical formulas of elements and or compounds that are participating in a chemical process in their most stable state. So please, if you do not remember those or you're not sure about how to do that, you need to go back to the chapters that dealt with these topics and learn this before you go on. Something else that we often also write in chemical reaction equations are the physical states of the substances that are participating in that process, if we know it. If we don't know the physical states of the substances, then we don't write those. But if we do know the physical states, then those are given as subscripts. Those are given as subscripts after the formula or the symbol of the substance. So in parentheses, S indicates solid, G indicates gas, L indicates liquid, and AQ indicates aqueous. Some people pronounce it as aqueous. That is a solution in water. Whenever you have aqueous, that indicates a solution, a homogeneous mixture with water. Okay, so here is an example of a reaction. When burned, solid magnesium reacts with oxygen gas to make a white powder of magnesium oxide. So when you're looking at a reaction such as this and you need to write a reaction equation, remember that you need to use the correct symbols and or chemical formulas of these substances and the physical states if you know them. For example, we know that we are starting this chemical process by using solid magnesium and oxygen gas to make a white powder of magnesium oxide. So it's very important for you to know what is the correct symbol for magnesium. Exactly, magnesium is an alkaline earth metal in group 2A, and in its elemental form the correct symbol for magnesium is Mg. What is the correct symbol for oxygen gas? Oxygen as a stable form does not exist in an atom form. Instead, it exists as a diatomic molecule. So this is something you must know. And creates a white powder of magnesium oxide. So from the name, you need to be able to write the correct chemical formula of this ionic compound. The correct formula would be MgO. Now, once again, I cannot emphasize this enough, guys. If you're having trouble writing the chemical formulas of substances, you must go back to the previous chapters and learn that before you move forward. Okay, so given those, the equation therefore gets written as MgS plus O2G gives us MgOS. Now note that the subscripts um, written after the chemical symbol indicates the physical state that these substances are either used in or produced in during the reaction. Some other terminologies to also get familiar with: reactants. Reactants are those substances that we start a chemical process with. These are the substances that are consumed during the reaction. These are the substances that are used up to create new substances. So in this particular reaction, there are two reactants, magnesium solid and oxygen gas. Products are those substances that are produced as a result of the chemical process. These are the new substances that are created as a result of the chemical process. And in this reaction, there is only one product, and that is magnesium oxide in a solid form. Now, there is no restriction as to how many reactants and how many products there should be in a chemical reaction. Given a chemical reaction, any number of reactants or any number of products could be part of that chemical process. Something else that you also need to know, that the plus sign only indicates and. So when we say MgS plus O2G, all we are saying is solid magnesium and oxygen gas. You could have, of course, also written that as O2G plus MgS, and it really doesn't matter because the plus is not a mathematical operation. It is just to say and. The arrow is also very important in a chemical reaction equation. The arrow indicates the direction of the change. The reactants will always be on the tail end of the arrow, and the products will always be on the head end of the arrow. So the arrow gives us the direction of that transformation. Okay, so let's try and write some equations for the reactions that are described below. Please pause the recording so that you can read these carefully and then attempt these on your own before we go on. Okay, so in the first one, carbon monoxide gas and magnesium they are produced when magnesium oxide and carbon are combined. So what are the reactants here? What are the substances that we are starting with? We are starting with carbon and magnesium oxide, MgO. Once again, correct chemical formulas are very, very important. Do we know at least in this state, do we know the physical states of carbon and magnesium oxide? Well, you kind of do, because if you remember, carbon in the periodic table can exist as a solid under normal conditions. It's stable. Magnesium oxide, of course, is an ionic compound, so solid. And these react together to make carbon monoxide gas and magnesium. And magnesium, of course, in its stable form is also a solid. Phosphorus trichloride reacts with water to make hydrochloric acid and phosphoric acid. So phosphorus trichloride, PCl3 plus H2O makes HCl plus H3PO3. Now, I cannot emphasize enough the importance of being able to write the chemical formulas correctly from the names of these substances. Guys, if you can't do that, you will not be able to do the problems in this chapter. Okay, aqueous copper 2 sulfate solution reacts with iron to produce an aqueous solution of iron 2 sulfate and copper metal. So copper 2 sulfate aqueous reacts with iron to make aqueous solution of iron 2 sulfate, AQ, plus copper metal, so that's solid. Combustion of tetracarbon decahydride, C4H10. This is something I would expect you to remember, that when you're talking about combustion reaction of a compound composed of carbon, hydrogen, and or oxygen means it reacts with oxygen gas to produce water and carbon dioxide. So this has to be known to you. When aqueous solution of silver nitrate and potassium chloride are added together, a precipitate of silver chloride is produced in an aqueous solution of potassium nitrate. Precipitate means a solid. The word precipitate implies a solid that is created as a result of a chemical process. A solid that did not exist before but is new as a result of the chemical process. So an aqueous solution of silver nitrate, AgNO3, AQ, reacts with potassium chloride. Aqueous makes a precipitate of silver chloride, that is AgCl, solid because that's a precipitate, plus an aqueous solution of potassium nitrate. Okay. Please make sure that you're able to write equations based on the description of the reactions using correct chemical formulas. Okay, so now there is something that is also very important when you write chemical equations, that the mass of the substances must be conserved. This is the law of conservation of matter, law of conservation of mass, that says whenever any process takes place, you cannot just create mass or lose mass. All the matter that you start out with must be accounted for with whatever you end up with. So that has to be conserved. For example, basically that means that the total mass of the reactants must equal the total mass of the product. This is extremely important whenever you write any reaction equation. So for example, if you take this equation where methane CH4 is undergoing combustion to produce water and carbon dioxide, and if we compare their molar masses, if we add up their molar masses, we see that even though we used a total of 48.05 grams of reactants, we ended up with 62.03 grams of the products. That is not possible. You cannot create matter out of nothing, nor can you lose matter into nothing whenever any process takes place. The total mass of the reactant must equal the total mass of the product. So, in order to do that, in order to satisfy law of conservation of matter, we must also balance reaction equations. Reaction equations, after you write them using correct chemical formulas, must be balanced in order to satisfy this rule. Otherwise, those reaction equations are not correct. So basically what we are doing when we are balancing reaction equations is that we are making sure that the number of atoms of each elements on the reactant side and the product side are equal. So that is basically what we are doing. We are accounting to make sure that we are not just losing atoms or gaining atoms and keeping track of that. When you are balancing reaction equations, there are a few things that you cannot do, and this is extremely important to keep in mind, that we cannot do. We cannot change the subscripts in the chemical formulas of the substances involved in that process, because what happens when you change the subscripts? If instead of H2O I wrote H3O, what happens? Yes, it's not water anymore. You have changed the identity of the substance. Then it's not, that is not allowed. Cannot do that. The other thing that you cannot also do is change the identity of the chemical process itself by adding or taking away reactants or products from the reaction equation just because it's more convenient that way. We are not allowed to change the identity of the reactants, not allowed to change the identity of the substances involved, whether as reactants or products, by changing the subscripts. Nor are we allowed to change the identity of the chemical process itself by either taking away or adding reactants or products to the equation. So the only thing that we can do when we are balancing reaction equations is we can change the number that goes in front of the chemical formulas of substances in that equation. This number is called the coefficient. That is the only thing we can change while balancing an equation. Let me give you an example. So here is that same equation we saw before, which we saw that was not balanced. It was not satisfying the law of conservation of matter. So when we are trying to start balancing this equation, keeping in mind the things that we cannot do. So this is what I do, and maybe you find this approach useful, and everybody has their own way of balancing equations. But what I do is, when I look at an equation, I take stock of all the atoms that there are in the reactant side. So if you add up all the carbons on the reactant side, that's 1. The total number of H's on the reactant side is 4. Total number of oxygens is 2. Similarly, take stock of all the atoms on the product sides as well. And you can obviously see that there are equal number of carbons on both sides. That is good, but hydrogen and oxygen atoms are not equal. So we do need to work a little bit to balance these. So remember, the only thing we're allowed to do is change the number that goes in front of the chemical formulas or symbols of substances involved. That number is called coefficient. If there isn't a number, then of course the implied number is 1. So here's my first step. I see that there are 4 hydrogens on the reactant side but only 2 on the product side. I added 2 in front of water in the product side, because when I do that, basically that changes the number of hydrogens on the product side to 2 as well, because this number 2 applies to the entire chemical formula H2O. So now their total number of hydrogens is 4. It's balanced, but because we added that number 2 in front of the entire symbol H2O, the number of oxygen atoms changes as well, because the 2 applies to the entire chemical formula. Now the total number of oxygen atoms on the product side is 4 as well. So the oxygens is not balanced now. Okay, so we try to therefore change the coefficient on the reactant side to try and balance that out. We put a 2 in front of O2. If we put a 2 in front of O2, please remember that that 2 applies to the entire O2 molecule. So now if we count a number of atoms, we have 1 carbon on both sides, we have 4 hydrogens on both sides, and we have 4 oxygens on both sides as well. Therefore, the final balanced reaction equation is CH4 2O2 plus 2O2 gives us 2 H2Os plus 1 CO2. If you now added up the masses of all of the substances, you will find that the total mass of the reactant does equal the total mass of the product. So this is a balancing process that you have to go through. Now balancing is a skill that gets better with practice. Balancing is definitely not something you can become good at, fluent at, by just observing. So please balance as many equations as you can come across. Practice this skill. So when you're balancing, please make sure you keep a few things in mind. Number 1, coefficients cannot be fractional. So if you ever come across a situation where you are forced to put a fractional coefficient in front of a substance, then do so, but then after you've balanced everything, multiply the entire equation by a whole number to get rid of that fraction. And I'll show you an example of that kind. Coefficients must be lowest whole number ratio. So if you are writing an equation where the coefficients are not the lowest whole number ratio, then you do need to reduce those down. And of course, this is a hint that that makes life easier sometimes when you're dealing with polyatomic ions. If you're looking at a reaction equation that has polyatomic ions both on the reactant and the product side, such that the polyatomic ions are retained, are not destroyed during the process, then keep those together for accounting purposes instead of looking at every atom separately. Let me give you an example of what I mean by saying that. So here is an equation. Calcium hydroxide reacts with sodium sulfate to produce calcium sulfate and sodium hydroxide. What I mean by this hint is that when you're accounting the atoms on both sides, so there is calcium, there's one, instead of breaking the oxygen and hydrogen of hydroxide, since hydroxide survives the process, keep it together. OH, there is two OH here. Sodium, of course, there are two sodiums here. Now similarly, sulfate survives the process, so keep it together. It makes life easier. There's one sulfate on the reactant side. If you do the same on the product, there is one calcium. Now there is one hydroxide, there is one sodium, and one sulfate. So you see that calcium and sulfate are already balanced. We need to work with sodium and hydroxide. We have two of each of those on the reactant side. So if we put a 2 in as a coefficient for sodium hydroxide, these become 2 as well, and the equation is balanced. So this hint might sometimes make the whole process of balancing equations easier and faster for you. Okay, so as I said, balancing is not something you learn by observing other people do it. You need to actually do it yourself. So please pause the recording at this stage so that you can work on these examples before you look at the solutions. After that, after you're done with that, I would encourage you very strongly to practice more before you go on to the next session. So looking at the first equation, Fe3O4 plus 4H2 gives us 3 ions and 4 H2O. Next one would be 3 sodium hydroxide aqueous plus phosphoric acid aqueous gives us sodium phosphate and 3H2O liquid. 2C4H10 plus 13O2 gives us 8CO2 plus 10H2O.